So I'll be going over section C. So as Daniel said, section C for whatever reason is weighted the least on the Beaver, but definitely it's probably the hardest. So it will like separate your scores from other people in that sense, even though it's weighted not very high. Okay. So the first problem is called spider car. In the fenced area shown, there are yellow cars and a single red spider car. AO is trying to get the spider car in the spider square just outside the fenced area. In one move, AO can drive one car forward one square, reverse one car backward one square, rotate one car left in its current square, or rotate one car right in its current square. There can only be one car per square, and only the spider car can be moved into the spider square. What is the minimum number of moves AO needs to get the spider car in the spider square? So this is another optimization problem, as the Beaver contest seems to really like. And in optimization problems, there's always going to be two parts. So first of all, you want to come up with a construction, right? You want to come up with a construction that works for a certain maximum value or minimum in this case. And then you want to prove, right? You want to show that you cannot do better. So in this case, in the minimum, right? That means you cannot get any smaller. So this problem, funny enough, is also kind of a two-part problem, right? First of all, we need to get the red car, the spider car, in the spider square. So we need to drive the car to the square. And then second of all, we need to move the yellow cars out of the way to clear a path for the red car, right? So this is a kind of a two-part problem inside a two-part problem, in that sense. So first of all, let's look at, because we know we need to get the car into the square no matter what, right? We need to drive it there no matter what. So we need, right? We need three right moves, and then similarly we need three up moves. And in between those rights and ups, we are going to need two turns, right? We'll be turning from up to right and then to back up again, right? So two turns. So that's already eight moves. And this is, we know we're going to need these 8 moves no matter what, right? Even if all the yellow cars were gone, we still need these 8 moves just to drive the car to the square. Okay, great. So we can put that aside now. And we only have to consider in how many steps we can clear the yellow cars out of the way. So first of all, right, we need to get past, this first layer. There's this kind of like L-shaped blockade. And we need to clear this blockade somehow, right? So the most optimal way is we can do this just in one step. So by moving this car here, one step down. That way, we can clear the path like so, right? And I'll just erase as I go. So now the second question is, how do we get past, the second layer of cars, the second L of cars? And you'll find that certain methods work better than others. So for example, right, if we were to say, oh, you see this car, right, is kind of in the way. So what if we turn this, we make it go one and then go one again. So two right, a turn and two right steps. Well, that's going to cost us 3 steps. So can we do better? And the answer is going to be yes. We can actually clear this blockade in just 2 steps, even though it might be a little unintuitive, because we can move this car right and then move this car down in 2 steps. And then we'll be provided with this path that we know is going to take 8 steps. So therefore, the correct answer is going to be 8 plus 1 plus 2, which is going to be 11, and the answer is B. So how do we know 11 is optimal? Well, we know we need greater than or equal to, we need greater than 8 no matter what. And therefore, the least possible is technically 9. But 9 clearly is not going to work, right? Because we can't just get all the yellow cars out in one move. So therefore, the answer has to be 11 once we found the example. Okay, let's keep going. So The second problem is called puzzle pieces. A beaver has a puzzle with 12 different types of pieces, 4 of which are red, 4 of which are yellow, and 4 of which are blue. There's an unlimited number of each type of piece. Using these pieces, the beaver can create various color sequence. Each piece in the sequence must have a flat left side, and each piece must have a flat right side. Pieces join the usual way, but 2 pieces can be joined on their flat sides, and pieces can be rotated. One possible sequence is below. Okay, so which of the following color sequences cannot be constructed? So let's just take a look at the answer choices, right? So for option A, yellow, blue, blue, red, blue. So we know we need to start out with yellow, right? So this is our first one. And then we need blue. So we can do 2, and then blue again, 3, red, 4, and then blue is going to be 5. So perfect. So we just constructed this. So that means this is not the answer because, well, we can construct it. So let's take it back. Now let's look at option B. Blue, yellow, red, yellow, red. So we know we have to start with blue, right? We have to end with red. And then we need yellow. So that pretty much leaves us with with this, because we can't use the end piece. And then it's going to be red. So wait, no, this didn't. So 3. And then back to yellow. So 4, 5. Okay. Yeah, the red is a bit hidden in there, but I hope you can see. So therefore, for a similar reason, since we just constructed B, it cannot be the answer. And for C, we need red, red, yellow, blue, blue. So red, we have to start here. Maybe I'll use a different color. So we have to start here, red. And then we need another red. So this has to be it. And then yellow, so we need here. And then blue, so either of these. And then so therefore we run into a problem, right? Because if we choose either of these, we won't be able to join it with the second blue. So in other words, we can't have the sequence blue blue, right? Because there's no two blue puzzles that fit together one after the other. And so therefore, we know option C is the answer. Okay, for sake of time, I'll keep going. Spreading the news. 12 beavers share news with each other using a network of wires as shown. 2 beavers can share news if they are directly connected by wire. For example, beaver 6 is directly connected to 7 and 10, but not to 3. All beavers want to hear news as quickly as possible. As such, a beaver with news uses all of its wires simultaneously to inform the other beavers that it is directly connected to. For example, if 8 has news, it will inform 1 and 11 right away. Then 1 and 11 will spread the news to 2, 4, and 5. The beavers continue to spread the news until all beavers have been informed. Okay. If there is news that should be spread as quickly as possible, which beaver should be informed of the news first? So just as a little aside, this is another graph theory problem, right? As you'll see, graph theory is a very, very common topic in computer science and mathematics, and is certainly being tested a lot in this contest. So here we're asked essentially to find the center of this graph in a sense, right? And yeah, this is very, very closely linked to breadth search, right? So we essentially want to find the vertice such that the distance from that vertice to all the other vertices is as small as possible, right? So let's just take a look at the answer choices. So for option A, right, if we were to have 1 as the center, hypothetically, then we see just visually looking at it, right, these beavers, 12, 6, and 7, are quite far away, right? And indeed, it's going to take us 3 steps to reach there for 12, 6, and 7. And for all the other beavers, you can reach in 2 steps or less. But that means, right, like this answer choice A is only good for 3 steps. So we can write 3 steps, right? It's going to take 3 steps. So let's keep going. So option B, right? Option B, just visually looking at it, it looks a lot better, right? Because it's more centralized. And we won't run into the same problem, because for 12, 6, and 7, we can get we can get it in 2 steps. And as you'll discover, for all the other beavers, right? So for 3, it takes 2 steps. For 5, it takes 2 steps. For 9, it takes 2 steps. 11, 2 steps. 8, 2 steps. And everything else is like 1 step or 1 step, right? So that means we can get option B in 2 steps. So that already eliminates option A. Now, let's take a look. Let's take a look at the other answer choices. So for option C, if we were to have 4 as the center, just visually speaking, well, this is awful, right? Because it will take us 3 steps again to reach 12. It's way too far. It just visually looks very far. So again, 3 steps. C is wrong. And then D, 10. Well, at first sight, it might look similar to 2, but you'll realize that, for example, from 10 to 11 is going to take 3 steps, right? So for similar reasons, 3 steps. So therefore, the best we can do is 2, right? In which we can get the message to everyone in 2 steps. Okay. The next problem is called Book Organizer. Bora uses a flowchart to organize her books onto 3 shelves. When she gets a new book, she starts at the top of the flowchart and follows its instructions to determine on which shelf the book belongs. Each diamond in the flowchart includes a yes or no question about the book's title. The answer determines which arrow leading away from the diamond Bora will follow. When an arrow points at a shelf, the book is added to that shelf. Otherwise, Bora continues to move through the flowchart. If Bora's books end up on the shelves as shown, which of the following questions could have appeared in the diamond marked with question mark? Okay, so yeah, this is like a flowchart problem, and a flowchart is a very, very common concept. It's like a very common way to represent things in math and computer science. So again, with a lot of these problems, right, we don't really have much of a choice other than to go through the answer choices one by one. So for option A, does the title include the word men? Well, if this were to go in the question mark, right, that means all 3 of these books here will have to satisfy this requirement, right? But we know, well, this is a contradiction because we know the book The Sixth, right, doesn't contain the string men. So therefore, this doesn't make sense logically. For option B, are there fewer than 4 words in the title? And even though right, even though this satisfies all the books in the yes category, right? These 3 they have fewer than 4 words in the title. It doesn't satisfy the no category because, for example, Frankenstein only has 1 word, right? And if the condition were true, then it would have 4 words or more, right? So I'll just write Frankenstein. So we can eliminate option B as well. Is the letter I in the title? Well, it fails right off the bat, right? Because 12 Angry Men, the very first book, doesn't have an I. So we can eliminate option C, therefore the only answer has to be D. And indeed, we can check that D does work because 12 Angry Men, the 6, 8 Men, 8 Men Out, they all have numbers. And Frankenstein, The Wizard of Oz, The Hobbit, The Computer, they all do not have numbers. So this makes sense logically, and by elimination, it's also the only correct answer. All right, for the final problem, train trip. This train has 3 carriages with the number of seats and luggage limits as shown. 8 beaver families would like to go on a trip, but every beaver must sit on its own seat. If one member of the family sits in a carriage, all members of the same family must sit in the same carriage. Family's luggage must be in the same carriage as the family, and the luggage weight has to be within the limits of each carriage. Details are given in the following table. Okay, what is the maximum number of families that can go on the trip. So again, another optimization question, right? I'm telling you, CMC and the Beaver, they really, really love optimization. So something we can start doing, right, is we can take a look at the total. So total, we can take a look at the total capacity. And the total number of seats, well, is going to be 6 plus 10 plus 15 is 31. And the total number of the total weight, I guess, allowed is going to be 160, 200, 300 is going to be 660. And if we take a look at the totals, right, for the families that were given, the total number of members, right? I'll just save you the computation, I guess. But I believe this is going to add up to 32 if you sum this column. And if you sum the luggage weights, it's going to be 660. So you just sum down the column, right? So what this means, right? Because if we have 32 people and there's only enough seats for 31, that means we can't have all 8 families, right? We can't have all of them. So immediately we can eliminate. So now the answer, well, the question is, can we get 7 families exactly? And the answer is going to be yes. So I'm going to show you one possible construction. So if we make a table, and then the number of people is 3, 5, 2, so the total is 10. And then here is going to be like 4, 4, and then 5. So the total is going to be 13. So, and then the weights it's like 50 plus 110 plus 40. Again, I just computed this ahead of time because it's just a lot of adding. And then here is going to be 80 plus 80 plus 100 is 260. And so if we take a look back up here, right, we care about the per carriage. So we have 6, 10, 13, and up here is 6, 10, 15. So that works. And then 130, 200, 260, 160, 200, 300. So perfect. So everything falls within the range. So therefore, this is going to be a valid construction. And the answer is going to be B. So again, optimization problem, right? We've found why we cannot have 8. And then we showed why we can have 7. So therefore, the answer is going to be 7.